Analytical Conics by D.M.Y. Sommerville. Section 4. Pole and polar. As in the case of the other conics, if x sub 1, y sub 1 does not lie on the curve, the equation y sub 1 equal 2a times quantity x plus x sub 1 represents the polar of the point x sub 1, y sub 1. Using Joachim-Thals' method, let K be the position ratio with respect to the points P equal x sub 1, y sub 1 and Q equal x, y of one of the points x or y in which the join of these 2 points cuts the curve. Then the coordinates of x or y are kx plus x sub 1 divided by k plus 1, ky plus y sub 1 divided by k plus 1. Substituting in the equation of the parabola, since x lies on the curve, we have quantity ky plus y sub 1 squared equal 4a times quantity k plus 1 times quantity kx plus x sub 1. Hence, we have the quadratic equation in k squared times quantity y squared minus 4ax plus 2k times quantity y sub 1 minus 2a times quantity x plus x sub 1 plus quantity y sub 1 squared minus 4a x sub 1 equal 0, whose roots k sub 1 and k sub 2 are the position ratios of x and y. Now, if y sub 1 equal 2a times quantity x plus x sub 1, we have k sub 2 equal negative k sub 1. Hence, x and y divide PQ internally and externally in the same ratio, and xy, PQ is a harmonic range. Hence, the polar of P is the locus of harmonic conjugates of P with regard to the parabola. Corollary. The relation which connects 2 conjugate points P equal x sub 1, y sub 1 and Q equal x sub 2, y sub 2 is y sub 1, y sub 2 equal 2a times quantity x sub 1 plus x sub 2. This equation expresses the polar of P passes through Q and that the polar of Q passes through P. Section 5. To find the coordinates of the pole of a given line. Let the equation of the line be Lx plus My plus N equal 0, and let P equal x sub 1, y sub 1 be its pole. The equation of the polar of P is 2ax minus y sub 1y plus 2ax sub 1 equals 0. Since these 2 equations represent the same straight line, we have L is to M is to N equal 2a is to negative y sub 1 is to 2a x sub 1. Hence, x sub 1 equal N divided by L. Y sub 1 equal negative 2am divided by L. Corollary. If the line L sub 1x plus M sub 1y plus N sub 1 equals 0 passes through the pole of the line L sub 2x plus M sub 2y plus N sub 2 equal 0, we have L sub 1 times N sub 2 divided by L sub 2 minus M sub 1 times 2a M sub 2 divided by L sub 2 plus N sub 2 equal 0, i.e. L sub 1 N sub 2 plus L sub 2 N sub 1 equal 2a M sub 1 M sub 2. This is the relation between 2 conjugate lines, and it is related to the tangential equation Ln equal am squared in exactly the same way as the relation between the coordinates of 2 conjugate points is related to the equation y squared equal 4ax. In fact, the tangential equation may be obtained from this relation by putting L sub 2, M sub 2, N sub 2 equal L sub 1, M sub 1, N sub 1, since 2 conjugate lines can only coincide if they are tangents to the curve. Section 6. Diameters. To find the locus of the midpoints of a system of parallel chords, let y equal mu x plus c be the equation of a variable chord in a fixed direction, so that mu is fixed while c is variable. Substituting the value of x in terms of y in the equation y squared equal 4ax we have mu y squared minus 4ay minus 4ac equal 0. A quadratic giving the values of y for the 2 points of intersection of the chord. If y sub 1, y sub 2 are the roots of this equation, and y is the ordinate of the midpoint of the chord, y equal 1/2 quantity y sub 1 plus y sub 2 equal 2a divided by mu. Hence, y is constant, and the locus of the midpoints of chords parallel to the direction y equal mu x is the straight line mu y equal 2a. As the corresponding locus for the ellipse or hyperbola is a diameter or a line through the center, we shall define a diameter of a parabola as a straight line parallel to the axis. There is no such thing as conjugate diameters of a parabola, but there is a direction or gradient conjugate to every diameter, such that all chords drawn in this direction are bisected by the diameter. The gradient conjugate to the diameter y equal b is 2a divided by b. Since the tangent at the end of a diameter is the limiting position of the parallel chords which cut the parabola, the direction which is conjugate to a diameter is that of the tangent at the ends of the diameter. Since the diameters of a parabola are all parallel, we can conceive of a parabola as the limiting form of an ellipse whose center is at infinity. In the case of the ellipse or hyperbola, a diameter is the polar of a point at infinity. This holds also for the parabola. The point at infinity on the line y equal mu x is 1, mu, 0. Substituting in the equation y sub 1 equal 2a times quantity x z sub 1 plus x sub 1 z, these values for x sub 1, y sub 1, z sub 1, and putting z equal to 1, we get mu y equal 2a. The point at infinity on the axis is x equal 1, 0, 0, and its polar is z equal 0, i.e., the line at infinity. Hence, since the polar of x passes through x itself, x lies on the curve, and the line at infinity is a tangent. This appears also from the equation of the curve written in the form y squared equal 4axz. For z equals 0 gives equal roots and is therefore a tangent. Analytical Conics by D.M.Y. Sommerville. Published by G. Bell & Sons, Limited, London, 1924. Read by Jim Renholt. Programming and illustration by Jim Renholt, 2022. Analytical Conics by D.M.Y. Sommerville. Section 7. The Focus. The focal property of the ellipse or hyperbola, fp plus or minus f prime p equal constant, breaks down for the parabola. But there still exists a focus directrix property, i.e. there is a point f and a corresponding line such that the distance from the focus f is in constant ratio to the distance from the corresponding line, the directrix. The equation y squared equal 4ax may be written y squared equal quantity x plus a squared minus quantity x minus a squared, i.e. quantity x minus a squared plus y squared equal quantity x plus a squared. But this expresses that the distance from the point a, 0 is equal to the distance from the line x plus a equal 0. Hence, a focus exists at the point a, 0, and the directrix is x equal negative a, which is the polar of the focus. Since the constant ratio is unity, we say that the eccentricity of a parabola is equal to 1. Analytical Conics by D.M.Y. Sommerville. Published by G. Bell & Sons, Limited, London, 1924. Read by Jim Renholt. Programming and illustration by Jim Renholt, 2022.